In this talk, I will present, on the basis of a very recent experiment, the two main views of physics today about how to explain the quantum world. One of these views is non-locality at detection. This means influences or agency coming from outside space-time, and in this sense, non-material agency. And the other view is the view of many worlds, assuming that actually there is not only one visible and material world, but many parallel worlds which cannot interfere with each other. The conclusion of the talk will be that if we keep to free will and to freedom, then in fact we have to assume non-locality at detection, and this means also non-material influences governing the world from outside space-time. The whole debate begins with a Gedanken experiment of Einstein in the Solvay Conference 1927. Einstein proposed this experiment. We have here electron waves impinging into this screen. Electrons are particles, but according to Louis de Broglie, particles behave also like waves. So Einstein says, let us assume that we have here waves of electrons impinging in this screen. Even if you have only one electron, this electron will behave like a wave. So, in arriving at this opening, this little opening in the screen, the electron will becomes diffracted in all possible directions. And this means that after this opening you have like spherical waves propagating towards this photographic plate here, or photographic film, where the electrons get detected. According to quantum mechanics, once the electron becomes diffracted in this opening, because he's propagating like a spherical wave, the probability of getting the electron detected in one point of this photographic plate is the same for each point of the plate. And this has an amazing implication, said Einstein, because suppose the electron becomes detected at the point P. Then this means that he cannot become detected in another point whatever of the plate. because there is only one electron, and then, because of conservation of energy, you have to get only one count. And Einstein said, well, that is amazing, because this means that, in a sense, all the regions of this plate are coordinated with each other in a non-local way, so that if there is a detection here at point P, immediately all other points of the plate, of the photographic plate, know that they cannot fire, they cannot detect the electron. So there is a coordination acting faster than light between all the points of the photographic plate, and Einstein said this is not possible because this is in conflict with the relativity. Relativity, said Einstein, forbids that in nature there can be influences faster than light. So he concluded this was an attack, actually the first attack of Einstein against quantum mechanics. He concluded that quantum mechanics cannot be correct and has to be complete somewhere. Well, this Gedanken experiment of Einstein to prove that quantum mechanics is not consistent, actually Einstein, after the Solvay conference, after 1927, he never repeated it. He withdrew toward another Gedanken experiment, the so-called EPR experiment or EPR paradox, which has become matter of debate, of intensive debate, since 1935. But once again, also Einstein presented this Gedanken experiment at the Solvay conference, and he never repeated it ever again. He preferred to argue against quantum mechanics on the basis of the EPR experiment. Why, we will see in the follow. It is amazing, but the experiment Einstein proposed in 1927 never has been done till this year. Some weeks ago, the experiment has been published in May, and the experiment has been realized at Geneva. Well, it was not exactly the same experiment. Instead of electrons, we use photons. This is particles of light impinging on a so-called beam splitter, a half-silvered mirror, where the light can go transmitted or reflected. Similarly, like here the electrons go diffracted in all possible directions, here the particles of light can go after impinging at the beam splitter, can go in two possible directions, transmitted or reflected. And if you put here two detectors, then these detectors play the role of the photographic plate. And the argument of Einstein is, if this wave arrives to this detector and to this detector, and this detector fires, then this detector doesn't fire. And this means there has to be a coordination between these detectors, like an agreement. If I fire, you don't fire. If you fire, I don't fire. Well, this agreement, if there is no disagreement, if there would be no coordination between these two detectors, then you would have the following situation. Let us call this detector A and this detector B for Alice and Bob. Well, then you would have the following situation. Suppose that there is no coordination. Then each detector fires on its own. The detector knows I have to fire 50% of the times, and detector B knows I have to fire 50% of the times when the information of the wave arrives, because here is a half silver mirror, so that you can say half of the light goes transmitted and half of the light goes reflected. So each detector knows it has to fire 50% of the times. But if they are not coordinated, then you will have the case where detector A counts, we represent this by 1, and detector B doesn't count. Or you will have the case where detector A doesn't count and detector B counts. But you could have also the case where both detectors count, one count in each detector, and also the case where no of the detectors counts. And because they are not coordinated, each of these cases can happen with the same probability. This means with 25%, and the same for this case, the same for this case, and the same of this case. This could be the prediction if these detectors are not coordinated. Well, now you can put these two detectors far away from each other so that you are sure they cannot communicate at the speed of light. So that if there is a communication, the communication would be faster than light, much faster than light. We have put these two detectors in the experiment in Geneva, so far away from each other that we could ensure this condition. Now, if all material influences are traveling in space-time no faster than light, that is at the speed of light or less, then since the two detectors are far away from each other, there cannot be any coordination. And then we should have the case where also each of these four possibilities should happen with 25%. Also the possibility where the two detectors fire together, and the possibility whether no one of the detectors fires. Well, the experiment performed in Geneva shows that these two cases never happen. So this means there is a perfect coordination, and if one detector fires, the other doesn't fire, and vice versa. Here we have a very interesting aspect that Einstein didn't consider actually. So Einstein put very much the accent in the fact that we have to have this coordination, and that this coordination happens faster than light, and therefore we have a conflict between quantum mechanics and relativity. He was focusing on this point. But there is another quite important point. You see, if there is no this coordination, if this coordination faster than light doesn't exist, then you could have the case where you have only one photon impinging on the beam splitters and two counts, one count in this detector and one count in this detector. Also, one photon, two counts. And this means that you are violating the conservation of energy. Complementarily, you would have certainly the case where no one of the detectors fires. And in this case, you have one photon and now count. You will say, well, in the average, the energy will remain conserved, but you are violating the conservation of energy in each single quantum event. You see that if you reject this coordination between the detectors, which is non-local, so faster than light, if you reject this, then you violate the conservation of energy. And so you see why Einstein withdrew from this argument against quantum mechanics, because if he rejects here coordination faster than light, then he is also rejecting the conservation of energy. This is not the case with the experiment Einstein proposed in the EPR experiment in 1935, where the conditions are so that he could argue against, he could attack quantum mechanics without rejecting the conservation of energy. So, once again, with our experiment performed this year in Geneva, we show not only that there is a non-local coordination between the detectors, that is, there is a non-material agency rolling the detections here coming from outside space-time, but, and this is a quite important conclusion, the experiment of Geneva shows that if we don't have this non-local coordination, this non-material agency rolling the detections, if we don't have it, then the most material property, conservation of energy, would not hold. So, to have the material property, the most fundamental principle rolling the material world, conservation of energy, to have this, we have to accept influences, agency from outside the space-time, non-local coordination, and this means, in fact, non-material coordination, rolling the detections between these two detectors. Now, you could object to this explanation that there is a coordination faster than light between these two detectors. You could say, look, there is no mystery. The beam splitter here works like a grid, and the light is composed of particles, consists of particles like bullets. So, if you are shooting these bullets against this grid, then you will have 50% going through and 50% going reflected. So there is no mystery that you get 50% here and 50% there. And for this, there is no need of coordination of faster than light coordination, of non-local coordination. Well, let us apply this objection, this argument, to another experiment. We expand this experiment to a so-called interference experiment. You have here a beam splitter, like here, and here you have two full mirrors reflecting all the light, all the arriving light, and guiding the light to this detector here and to this one here. So, if we apply this model of bullets impinging upon a grid, then you will say 50% here and 50% here, and then from this 50% you have 25%, you have 50% here and 50% here. So at the end, you would have 50% and 50% like here. But suppose now that we put here another beam splitter like this one. Then let us apply this reasoning. 50% going so, and arriving here you will have 25% and 25%. And the same for the other path. 50% arriving so, then 25% goes through to this detector and 25 goes through to this one. So at the end you will have again, if you apply this reasoning, 50% here and 50% there. If you do this experiment, you then get this result. You then get 50% here and 50% there. You get 100% in this detector and 0% in this one. That is an interference phenomenon. And now you could even change the length of this path, putting here convenient mirrors so that the light is going so through a longer path, and you could progressively change this length of this path. Then you will observe this. You will observe the following distribution of counts. For this detector 1, when you change the length of this path, you will go from 100% to 0% and then up again to 100%. And for the other detector, you go from 0% to 100% and you come again to 0%. So what means this? This means that each detector takes account of the length of the two paths. So if you have to assume that light is behaving like waves and not like bullets for reaching these distributions. But then when you are detecting at the detection, then you have single firings. You have like if you would have bullets. So in any case, you see, each detector takes account of the length of the two paths, and in order, so each detector will fire, for instance, this one, if the length is convenient, 75% of the times, and the other one receives information about the two lengths and knows he has to fire 25% of the times. But in order that one fires and the other not, then there has to be an agreement between the two detectors. So in any case, we have this coordination between the detectors, and like the experiment in Geneva shows, you can put these two detectors far away from each other, and this coordination is still there. So we need really non-local coordination, and this means something coming from outside space-times, some influence, which rules the firing of these two detectors. Well, actually, you see that these conclusions you cannot escape if you assume that there is a decision at the moment of detection. That is, that which detector fires is decided at the moment where the detection happens. And therefore, one detector has to take account of the other. And if the detectors are far away from each other, then this coordination happens from outside space-time. There is a way to escape non-locality, in this case, assuming decision at the beam splitter, but not only like if you have bullets, but if you have like a combination of bullets and waves. This was the idea by Louis de Broglie with his model of the empty wave, also called pilot wave. Louis de Broglie presented this idea also, or proposed this idea also, around the Solvay conference in 1927. The idea is the following. When you have a particle wave, for instance, of light, arriving at the beam splitter, then at the beam splitter there is a choice. The particle goes, for instance, this way, and the wave the other way. But this wave here, this wave, is an empty wave. This means it is a wave that doesn't carry energy and momentum. It is, in this sense, a wave you cannot observe, you cannot detect, because this wave will not interact with any particle other than its particle. Let me see. If you, with this model, you can explain interference, because you will have the particle going so and the empty wave going the other way. Then, when the particle and the empty wave meet again at the second beam splitter, the empty wave will guide the particle according to the information about this path it has, so that at the end you will get also these distributions here with decision at the beam splitter, but at the price of having an entity, the empty wave, which is a weird entity, because it is an entity traveling in space-time, like a particle, but an entity you cannot observe, you cannot detect. So you cannot access this entity directly. And it is in space-time. You see, there is here a crucial difference. In the case of decision at detection, of non-locality at detection, we are assuming that there is an agency coming from outside space-time. So the quantum correlations, the quantum effects, come from outside space-time. And in this sense, these principles ruling the detections are not directly accessible. You know they exist because you see the correlations, you observe the correlations, but you don't access directly these principles which are outside space-time. In the case of the empty wave, you are assuming an entity existing in space-time. So, but the space-time is the domain of the visible. For instance, light defines the space-time. And the space-time is defined through the velocity of light. And the light is detectable. So you can have a detector of photons. So in this way, you are assuming that all what exists in space-time is visible, is detectable. The empty wave, however, propagates in space-time, exists in space-time, but it is not directly accessible. This is there is another point also when you assume that these empty waves are, when you assume these empty waves to explain the quantum phenomena, you can escape locality in this experiment because the decision happens at the beam splitter. But you cannot escape non-locality. You cannot escape non-locality in other experiments, like the experiments like John Bell demonstrated. So John Bell demonstrated that even assuming empty waves, you will have a criterion for escaping, for refuting locality. I will now enter in the details of this issue. These are very well known in experiments, the experiments violating the Bell inequalities. But the issue is that these experiments, what I will stress is that these experiments refute models, local models, assuming the empty wave, the local empty wave. Because otherwise, if you assume decision and detection, you prove non-locality in a much simpler wave. This is the point that the theorem of John Bell addresses. Models which assume the pilot wave, the empty wave of de Broglie, and then they are assuming decision of the beam splitter, and if you have entangled particles, pairs of particles, pairs of entangled particles, then even if you assume decision at the beam splitter, you can you will show that even if you assume decision at the beam splitter with the empty wave model, you will have that this decision, in case of experiments with entangled particles, this decision at two beam splitters far away from each other will also be correlated at a distance. So that even if you assume empty waves and decision at the beam splitter, by the Bell theorem, in other kinds of experiments, in other type of experiments, you will prove that locality is wrong. However, the issue has another aspect, and is the following. Because when you assume empty waves, so you assume that there can be entities in space-time that you cannot detect, and that they are not observable, then you can expand this model to the so-called many worlds view, first proposed by Everett. And already John Bell said that he suggested that many worlds is nothing other than a further development of the idea of the empty wave. And this is because if you assume, for instance, that in this case there is at the beam splitter there is a choice with the particle going this way and the empty wave going this other way, then many worlds say, actually, what splits is not only the impinging particle wave into a particle and an empty wave, but there is another splitting also. It is the whole world what splits. So that there is a parallel world which is not accessible to this one. There is a parallel world where things happen in the alternative way. Here, in the parallel world, the particle is going this way, and the empty wave this one. So that, you see, you can explain things with this model of the many worlds in a absolutely local way, and you don't need non-locality, and you don't need influences or coordination coming from outside the space-time. Every time that there is a choice or a decision, actually there is no decision, but all possible decisions happen. What is that they happen in different worlds. And this world is not accessible to this one, and vice versa. The same way that the empty wave is existing also in space-time, but it is not accessible. It is not something we can observe. So you see, the idea of the empty wave is when it's led, if we assume the empty wave, we are led to the many worlds picture. And this is particularly clear with the new version of many worlds proposed by Gilles Brassard and Paul Raymond Robichaud. They call this version parallel lives. And this is this is nothing other than to say that in the space-time you have different regions. You can have parallel regions which are not accessible to each other, but they realize all possible alternative outcomes. Well, at the end, so we have to decide. We have to choose. We can have a decision at the detection and then accept non-locality at detection, non-local coordination of detections coming from outside space-time, and in this sense non-material influences, or you can assume many worlds or parallel lives in which actually you have no decision, because at any time that there is a beam splitter, all possible outcomes become realized, even if they become realized, but they become realized in different worlds. If you assume non-locality at detection and non-material influences, then you can have free will, you can have decisions, you can have choices, freedom. If you assume many worlds, then actually there is no choice, there is no free will, there is actually no freedom. This is so the two alternatives we have, the two main views we have to which quantum mechanics, to which we are led if we study the quantum world. The standard view in quantum physics is to assume non-locality at detection. And so I think it is a very sound view which fits very well with our feeling that we are free, that we can make real choices, and also that we have a personal identity, that we have then also rights. And so it seems me to be important, the issue, if you wish to claim for your rights, to define your rights, then it is necessary that at the end we accept the standard view of quantum physics, assuming non-locality at detection, and assuming also a visible world which is to some extent ruled by influences coming from outside space-time, in this sense, non-material principles. Thank you very much.